Um, yesterday, after the lecture, some of you came and basically told me that I've been asking you for 3 whole lectures to hold your breath. Okay? And I couldn't agree more. Yes, I've been asking you to hold your breath. I'm going to be asking you to hold your breath even for 1 more hour. Okay? Hopefully you won't die. And then hopefully, at the end of that hour, we're going to see where we're going to land. Okay? That's not very different from when you do research. When you do research, you also start with some intuition of where you want to go. You have some basic principles, and you just do your math. As also somebody said yesterday, that you have been able to follow the math, but sometimes you get lost. Well, that also happens. And then you just keep pushing, and you hope for the best that at the end something nice will happen, and you will recognize something that you want to get. Okay? So let's recap a little bit the whole story from the beginning. It's a big summary. Okay? So we started the whole story studying the differential cross-sections. This sigma equals to this object times this d-ellipse integral, or this d-ellipse differential, divided by EAV times V. Okay? I think I left you as an exercise to compute the dimensions of M. Did anybody do it? I'm sure you all did it. So, but let's actually do it quickly here, just to check the algebra. Okay? So the dimensions of sigma are dimensions of inverse of mass square, right? Because they are dimensions of area. Sigma is an area. The dimensions of 1 over EA, EV, V are also dimensions of mass square. Here, C is equal to 1, so velocities are dimensionless. So we have dimension of 1 over mass square. Okay. How about the d-ellipse integrals? Well, for that, or the d-ellipse differential, we have to remember what it was. It was the product from 1 to n, d4p, a, we had pa squared, or pi squared minus m squared, and we had an overall momentum conserving delta function all over there. So let's compute the dimensions. So this guy gives us mass to the 4n. These guys, we also have n of them. Each one of them gives us a -2, so we have an n, right? And we only have one of these guys, and this guy will give us an m-4, okay? So in total, our d-ellipse has dimensions of 2m-4, okay? Now, looking at this equation, that implies is that the dimensions of our matrix element are what? Well, they have to balance this equation, right? So these two guys cancel each other in the equation. So we need something that cancels this, but the matrix element is square, so we can remove the 2 and put a minus sign. So the dimension is minus n-2. Yes?
So wasn't there a factor of 2 with each of the energies?
Thank you very much, but yes. Very good. Okay, so we have that. Now, you won't see this like this in places where they compute this dimension because they like to define it in terms of the total number of particles. So let me call n total the total number of particles which is equal to, in our case, 2 plus n. These two are A and B. So this is the total number of particles involved in the whole process, including the incoming ones, okay? That's a formula that people like to write. And you should know why, right? Because due to crossing, who is incoming and who is outgoing is also up to us somehow, right? So it's better to talk about the total number of particles involved in the process, okay? So according to this, if we plug that in here, we get m. These have dimensions of mass to the total number of particles minus 4, okay? Very good. So that's probably what you got, right? You all did the exercise, and you got this. You didn't have a motivation to define this, but this is the new part that I'm adding. Okay. Next, we move into unitarity. And in order to discuss unitarity, I'm going to concentrate on the case when we only have two external particles, two outgoing particles. So we have particles A and B coming in and producing particles. So I'm going to change my notation. This was convenient to label the outgoing particles from 1 to n when we had any number. But if we only have two, we might as well give them names, just like these ones. So we can call them PC and PD, so particles C and D. So unitarity told us that in the limit, when PA plus PB squared goes on shell, when PA plus PB goes on shell, meaning that the square goes to m squared, this object has to behave, or it has to factor, it has to factorize as two processes where these two guys come, produce Q. We have 1 over PA plus PB squared minus m squared. We got the I epsilon. Of course, the I epsilon sometimes can be dropped. Epsilon is something that is very, very small. At the rational function approximation that we are working with, we can drop the I epsilon. Yes?
So probably a minor point.
Yes.
You keep on saying that limit as the mass shell, but we have two particles. So would it be 4m squared or this 1m?
Sorry? No. No, that's very, very important. We're tuning our experiment, okay? So that the momenta of these two particles add up to be the momentum of a physical particle. That almost never happens. But again, so that would be very, very complicated to engineer, right? But we are theorists, so we can just imagine that we are setting the momentum of the two incoming particles so that when they add up, they are very, very close to the momentum of a physical particle, which I'm calling Q, by the way. Yes?
I think I missed, why do we have two outgoing particles now?
Because I got tired of writing from 1 to n. Oh. Yes, sorry. Yeah, you said it, but maybe I should have said. So, okay. Take n equals 2. Well, take n equals 2. Yeah, no, I should have said it. Yes, I should have written that we're going to consider the case n equals 2. Okay? So we are missing something important in this equation, which is the other side. Q goes to PA, sorry, PC and PD. Okay? The next thing we discussed was crossing. Okay, in discussing crossing, we realized from experiments that if we compute this rational function that describes this process, if we were able to compute it, then the same rational function would be obtained if we were computing the process where particle C was incoming, and we replace its momentum by minus. And here, say, we leave PB. Actually, let me leave here PA and bring here minus C and put here minus B. And here, let me keep PD, okay? And it would also be equal to the same rational function obtained by computing this process and then evaluating on the following momenta, PA minus PD PC minus PB. Yes?
Isn't there an I missing in the propagator there?
Yes, there is an I missing in the propagator.
It's irrelevant? Okay.
Yes, so here we're reviewing general principles.
Okay, and the second thing.
Everything modulo I, factors of 2 pi,
Okay.
yes.
So the choice for n equal 2 makes the m dimensionless, right?
Yeah,
Is
that now you got it. Yes, that's going to be nice for us.
What's the importance of that? Of this case that we're m dimensionless?
Nothing at this point. It's just that.
What makes m dimensionless?
Well, n choosing n. He noticed that n equals 2 seems to do something nice. If you look at the formula for dimensions, it makes m dimensionless. That sometimes is cool. I mean, you see something dimensionless, you say, oh, that might be more important than other things, perhaps. Or perhaps it's going to be easier to understand things in that case. Let's see. Okay? At this point, it's just an observation that for n equals 2, this is dimensionless, which is definitely true.
So, and one more thing. Q is a particle, a virtual particle. We're basically introducing it for the purposes of conveying. It's an intermediary.
Well, you see that in my computation of unitarity, precisely it's not I tune my momenta so that the momenta of particle A plus PB
Form Q and then Q.
add up to be the momentum of a physical particle. And when that happens, unitarity tells us that at least in this approximation, that the S matrix, that the matrix elements should factor as if these two guys were coming in and producing a physical particle. Q is a physical particle. I haven't talked about virtual particles anywhere, right? Yeah, in fact, that was the whole purpose. I don't want to talk about virtual particles. This is all physical, right? Okay, so by doing this and combining with unitarity, we know that this rational function has a pole of the form 1 over PA plus PB squared minus m squared. And this quantity is what we call S. Okay? In this case, we get a pole of the form, so maybe I should define it here. So S is going to be PA plus PB squared. We define T to be PA minus PC squared, and U to be PA minus PD squared. So here we're going to get a pole of the form, and here a pole of the form U minus M squared. Okay? So crossing tells us that the same rational function must have all 3 poles. Yes?
So why don't you consider the diagram to be produced by having 3 on one side and 1 on the other?
Yes. So you mean in which case to do what? To study unitarity?
Well, I mean, crossing would presumably also tell you that those are also equal, so why don't you pick those poles as
Yes, because the unitarity constraint doesn't teach me anything in that case. Remember, the pole, we got this by comparing the two sides of the equation we got by imposing unitarity of the S operator. So try to do that when you have only one state coming in. You will find that the two sides are equal as a tautology. They are just identical, so you don't learn anything. So you have to put at least 2 on one side in order to learn something, okay? That's a very good question. And in fact, I encourage you to play with what we did in this course and change things. and see. In fact, I told you as an exercise that you should try to consider the next term in the unitarity expansion we did, right? We got this equation by studying the one particle exchange. So somebody asked, what happens to the zero particle exchange? Well, consider that one too. But the exercise you should really do is to go to the next case where you have two particle exchange, okay? So that one will imply that you have logarithms in your amplitude, or you should have logarithms too. Now you go to the three particle exchange, and that one will imply that you have other things different from logarithms and so on, okay? But in our rational function approximation, this taught us that our object, whatever it is some numerator, but it has three poles. Okay? That much we can learn from unitarity. All right, so what else? We also have discussed the constraints imposed by Lorentz transformations. Okay, and here I'm going to restrict myself to the case of massless particles.
Just one question.
Yes?
Everywhere we've only switched either taken C or PD to the other side. What if we took both of them as incoming and A and PD as outgoing? What's the point?
Remember that everything that I'm doing here is on the support of momentum conservation. So this must be true. Okay? And you can see that given that this relation is true, if I pass A and B to that side and C and D to the other side, I don't learn anything new. I only learned that there is a Pauling 1 over S, but I knew that already.
Okay.
You see that S is PA plus PB. If I switch these two guys to one side and bring the other guys to the other side, I learned that there is a Pauling 1 over PC plus PD squared. But that was S again, because of momentum conservation, indeed. Very good, so you're doing the exercise already. Checking, trying to change everything that we have said. But this is important. Everything we're doing is on the support of momentum conservation. Okay, so Lorentz transformation, we decided to study, well, I decided. Sorry. We're only going to study massless particles today. And in order to study massless particles, we found that there was a nice way of describing the momentum of all particles, and it's the following. If P is a null vector, we can replace the momentum of a given particle and describe it by a pair of spinors with indices going from 1 to 2. Okay? And in the tutorial, you were asked to show the following, that if you take the determinant, say, given two vectors, P mu and Q mu, which are null, and the corresponding spinors, lambdas and lambda tildes, you were asked to show that this quantity this determinant was invariant under multiplication by SL to C, okay? And people call this, I told you yesterday, They call this P and Q. Now, of course, when you want to write this down explicitly, you don't write determinants all the time, right? What you do, really, is to write lambda P with an index alpha, lambda Q with an index beta, and you put something called epsilon alpha beta. What is epsilon alpha beta? It's an antisymmetric, yes, tensor. Well, when you say tensor, you have to say how it transforms under something. And well, it transforms, it's a tensor, yes. I say, well, no. Then I stick with metrics. But indeed, it's a tensor, and it transforms with respect to SL2C. But this is the definition as a matrix. Let's forget about technicalities. It's just a, so you agree that this computes the same thing. I'm summing over alpha and beta, right? This, with this matrix, computes this determinant. Okay? Yes?
Before you go on, yesterday we take P squared to be M squared, right? And we made massive particles, and for M0 we did massless particles, and like search for the representations of the Poincare group, right?
Yes.
But I can have P squared equals 0, and I can choose my first component to be positive or negative, right?
Yes.
That will lead me to two different representations.
Yes, so that would be correlated with the sign. Remember, I said that.
The sign of the
Right, the sign of P0 is Lorentz invariant as well.
Yes, but if P mu is real, this implies that the lambda of P has to be correlated with a lambda tilde by complex conjugation. But I also said that there could be a sign.
Okay.
This sign is precisely that choice, whether P0 is positive or negative.
Right, so the point of, well, maybe I'll ask you afterwards.
Okay.
But the other question that I have is those lambda P are defined, if I take the representation of SL2C of SL31 into SL2C, right? I mean, the spinor representation, which is.
Yes. So I think I know where you're going. These lambdas, just as abstract lambdas that don't have to do with momentum, we can think about them as being they are in the fundamental representation of SL2C. They are spinors, right. And SL2C can be thought of as a double cover of the Lorentz group. That's fine. Right? But we want to do more. We want to extract more juice out of these guys than just that. So we define a reference. Remember that they are defined up to an overall scaling, right? So we define a reference spinors corresponding to a given reference vector. Right. And from that, we deduce that we can make them transform as if they were particles, massless particles of helicities plus a half and minus a half.
Right. But the thing is that the only way I can somehow have information about helicities with the unitary representations of the Poincare group, right?
No, that's in the exercise I gave you.
Right.
There was an exercise to show that some particular transformation into SL2C of the reference Lorentz transformation that took you from K to P would be related to the SL2C representation of the Lorentz transformation acting on the standard SL2C transformation corresponding to taking K to P.
Yeah.
Okay? So do the exercise and you will find the answer to what you're asking. Okay? If not, ask me at the end of the lecture. Well, you can ask me at the end of the lecture and I'll tell you, do the exercise. But if you want to hear it again, I'm happy to say it. Okay, so the same thing for lambda tildes. And in that case, we have people like to write this. Remember, the dot only means that it's in a different representation of SL2C, but it doesn't matter. It's the same definition for the determinant, and this is called PQ. Now, according to this definition, there is some properties we should remember. So first of all, what happens if I exchange the labels? This is a determinant, right? So what happens if I switch?
Change by a sign.
You get a minus sign. Same thing for these guys. Okay? That's just a trivial consequence of the construction. Okay? Very good. Now, the last thing I want to say about the Lorentz transformation is that the trick we use, or why these things are useful, is that now our matrix elements are going to be rational functions of these invariants under SL2C, okay? But which we trick them into picking up phases under the Lorentz transformations. But all that discussion can be summarized by saying that we need our matrix elements yep, okay. This is not the one I want to use. This is the one I want to use. Okay. So if we have our matrix element that has lambda A tilde with helicity HA, lambda B tilde. Well, note that I'm not very consistent with the place I put the label A or B, right? If I'm forced to show you explicitly the label alpha and beta here, meaning the index of the spinor, then I bump up the particle label. If I don't have to show you the spinor index, then my preference is to put the particle label down. Don't ask me why, it's just somehow automatic. So even if I try to change it, I don't think I'll be able to do it in. So we have this matrix element, okay? And this is supposed to be a function of AB, AC, AD, and so on. And the same for the square brackets. Okay? It's a rational function of all these objects. Now, having the correct Lorentz transformations is equivalent, or is in order to have the correct Lorentz transformations for this rational function to have the right to be called a matrix element for this process, the following must be true. And it's all that must be true. We don't need anything else. If we rescale this spinor by some quantity TA, and this one by the inverse, same thing here. Okay? Our function, so this is what it's supposed to be. Okay? So when we perform that rescaling, this is just a rational function. So we will see factors of t coming out all over the place, right? Because we're just making that change. In particular, if we make the change on AB, what happens to AB under the rescaling?
Multiplies by lambda.
It goes into? That's right. And if I have AB, this one goes into? You said a star, but here I'm allowing T to be anything. It doesn't have to be a phase. As long as it's an inverse, I'm fine, right?
But didn't we say yesterday we only allow phases if we want the K to be dimension?
And that is if you want the momentum to be real, but
We don't want
why would you do such a thing? I mean, just because, just because we think we live in a space that has real momentum doesn't mean we have to restrict ourselves to that.
Fair enough.
Well, this has a nice consequence, right? If you have AB times AB, where does it go to? To the same thing. So this is an invariant. In fact, you should recognize what this was. What is that? PA times PB. That's right. So let me also write it. Let me also write it here. So 2 times PA dot PB. You should have found that it was equal to AB. So that was in the tutorial. So this is a Lorentz invariant. In fact, this is S from our definition. Okay. Okay. Now, this function, whatever function it is going to be, it's going to have a chance of being correct if it transforms like TA to the 2HA, TB to the power 2 times HB, TC to the minus 2HC, and TD to the minus 2HD times the object without the rescaling. Okay? So that's the statement. So our job is to build functions that do that. So in the tutorial, you were also asked to consider or to study the kinematics of the scattering of 3 particles, yes? Sorry?
With the T's and TV's commute.
The T's and, sorry?
Do they commute?
Do they, they are numbers. They are complex numbers. So no problem. Yes. Yes.
Just a quick question. So these scaling come from the bra and the cats? The bra.
Yeah, this is, our object is a rational function of these guys. When you perform the scaling, whatever function it is, in other words, suppose that somebody comes bragging saying, look, I computed the 10-point amplitude that nobody has ever computed, and they give you a rational function of these guys as the answer. Then you say, oh yeah, let me just check a little bit. And then you check the scalings, okay? And if they don't work out, you say, look, go back to the drawing board. That's not correct, okay? If they do, then you say, okay, it still has a chance. But let's check unitarity and see if it passes the test, okay?
So can you repeat why does the helicities come out as the powers in the?
Well, because we found that massless particles with a helicity HA, right?
They transform
Under Lorentz, right? They should pick up a phase that is an angle multiplied by the helicity. So if you want to think about the TAs or the T's, think about TI as being e to the I theta lambda pi. If you plug this for I, A, B, or C, or D, you will find the transformation we talked about yesterday.
Then I'm a little bit confused because we saw that the way the momentum vectors transform under Lorentz transformations, right? For massless
The momentum vectors are,
right.
sorry.
I have a massless particle, and under a Lorentz transformation, it transforms with that e to the I theta times the helicity, right?
Not the momentum vectors. You mean the states
Right, the
defined
states,
by,
yeah.
yes, that's right.
But
So that's,
we obtained that looking at the unitary representations of the.
no, look at your notes. The last equation we wrote down was basically this one. The only difference is that these guys were on the other side. And these guys were lambda PA here, and these guys were on the other side. Okay? So check that, please. But this is a statement that one has to check that it works. Yes?
Are we saying multiplying by some number is the same as some Lorentz transformation?
No, multiply by, I didn't say what the t's are just rescale like crazy. Just put t's all over the place. Don't even say what the t's are. Just check that the function that they are giving you is correct. Imagine I claim, just to give a quick example. I claim that I have a particle, or the scattering of a particle with helicity 1 here. Particle A has helicity 1. And I tell you that the answer is a rational function that doesn't have A's anywhere except here. Okay? It's some crazy function of CD and so on. Okay? I claim this is the answer. I come and tell you, look, I computed this is the answer. Then what do? You say, okay, let me check. If I rescale the function by TA, in fact, this is so cool that you can even check one particle at a time. You see, the t's are all independent. So you can set all the other t's to 1. So don't do anything. Just check that particular guy. So you do TA inverse lambda A tilde 1, and you put it in here. So you apply that transformation to this function. My assumption is that nothing else depends on A. That person came and gave me this function where A only appears here. So I used my transformation and said, okay, this looks like TA to the minus 1 times the same function, right? So is that correct? No. No, it's not correct. She said, no, it's not correct. You're missing something. Yes.
So the question kind of, I think, the formula you wrote down in last class had the helicities in place, but only when the underlying transformation was a Lorentz transformation. But here you're doing a rescaling of the lambdas.
Yes.
And I think that's probably what the confusion is.
All I'm saying is that ensuring that your function will have the correct transformations is equivalent. It's equivalent to the following statement. Once you have a function that does this, and you sit down and do your Lorentz transformation very carefully, painstakingly, with all details, your function will work. Okay? Okay? So this is the condition that we have to impose. All right. So let's see this in action. I mean, that's why we bothered to introduce it. In the tutorial, you were asked to study the kinematics of 3 particles. Okay? So say you have PA plus PB. In the tutorial, you had plus PC, but here, just since we're not using crossing all the time to put everybody on the same side, let me just stick to this notation. Okay, we're going to have 3 vectors, A, B, and C. Momentum vectors. Any vectors. Okay? Any relation of these labels with the labels we have used before are pure coincidence. Okay? And these A, B, and C have nothing to do with the labels we had in the previous. In fact, okay. Let's make 1, 2, and 3. Okay, very good. No chance of confusion. So did you check that P1.P2 was 0? right? The way you do it, well, it's almost given here. You square this side, and you square this side, and you get 0 because this is 0, right? But you can now move this guy to the other side and put this guy here, and then square again, and you get 0 again. So P2.P3 is 0, and P1.P3 is also 0, okay? Now, does that mean that we cannot do anything with our amplitude? Does the amplitude simply vanish? Well, as you were told in the tutorial, that's the reason we don't consider these amplitudes. Or in general, people don't consider these amplitudes because there are no invariants that can make them up, okay? But let's use this equation. So if we use that equation, we find that this is the same as the bracket 1, 2, and 1, 2 equals to 0, 2, 3, 2, 3 equals to 0, and 1, 3, 1, 3 equals to 0, okay? Now, when you have the product of two things equal to 0, you realize that all of a sudden there are two solutions, right? There are two solutions to this equation in principle. This can be 0 or this can be 0. You would say that's nonsense because we know that the lambdas are related. For any reasonable person who thinks that momenta are real, if one vanishes, the other one has to vanish, right? But you say, well, this is so tempting. Look, I have two solutions. then it's very hard to resist. You simply say, forget it. I'm going to consider complex momenta. I don't care if people say that I'm crazy or not. That's fine. I'm just going to do that, and I won't tell anybody that. I mean, that's another approach. Unless I find something interesting. And then if you do, you go back and tell people, look, I found this. How do you get it? Well, you know, you have to... That actually happens. Okay. So I'm going to consider complex momenta. That means freedom for these guys. These guys don't necessarily have to be related to each other. Okay? Okay. Well, if that's the case, then I have two solutions. Isn't that great? So either this is 0 or this is 0. And the same thing here. Or so you would think we have many possibilities, right? We can choose this, this, and this, or these three, or these three. Is that correct? How many possibilities do we really have? We have to make 3 choices, right? And only 2 possibilities in each. So 2 of them will necessarily coincide, right? Say I choose this one and this one. Okay? Now think about these lambdas as being little vectors in C2, in the 2-dimensional complex plane, right? The determinant equals to 0 is telling me that they are collinear, right? They are proportional to each other. If 1 is proportional to 2, because it's 0, and 2 is proportional to 3, what happens to 3 and 1? That's right, so this must be true, okay? And the same thing for this one. So I cannot choose mixed solutions. I can only choose all lambdas proportional to each other, or all lambda tildes proportional to each other, and therefore I conclude that I only have 2 solutions. That's very powerful. Let's see why it's powerful, okay? Let's try to combine this with Lorentz invariant, with this condition, okay? And see how far we go. Let's do it here. So we want to consider, I'm getting tired of writing the m's all the time, so let's use a nicer notation of just drawing the blobs, okay? And we have particles lambda A tilde with helicity HA, and lambda B tilde with helicity HB going into, again, say 1, 1, 2, 2, and 3, 3, H3. Okay? Now, our friend here can only be a function of the brackets, right? Of these brackets. But we concluded that due to momentum conservation, it can only be a function of the guys that don't vanish, right? When the other ones will not be there. So whatever this is either a function of only 1, 2, well, in the first case, where these guys vanish, then it must be a function of these guys, or a function of only these guys. Okay? Very good. So do you want to do an example, or do you want to just work out the general case? What's your preference? Oh, the general case. Who wants to do an example?
Which one's more
We can do both. We're free this afternoon.
Yeah, we can go until tomorrow. You don't have to do anything on the weekend, right? Well, let's do an example. Here it is. I'm only going to write the helicities. So this one is +1, +1, +1 here.
So just checking, everything you're doing now is on the support of P1 plus P2 is equal to P3, right?
Yeah.
Okay.
Yep, just as I said there.
Okay.
Nothing will, yeah. I'm willing to go from real momenta to complex momenta, but I'm not willing to go outside of momentum conservation. That would be really crazy. Yes.
How much did you, when we switch to complex momentum, we still have a relation between lambda and lambda tilde.
No.
There's no relation anymore.
No, not relation.
Arbitrary. They're not just related by some scale.
No, lambdas and lambda tildes are now completely arbitrary. Of course, we can still rescale one by something and rescale the other one by the inverse, and the momentum will not change. So we still have to keep that into account. Right? Okay, but now let me declare that we're going to try this one first. Okay? So can anyone come out with a rational function of only these three variables that scales correctly? So the function has to do the following. We have to rescale. If we rescale these objects by, now we can see what we want to do. It only depends on the lambdas. So this guy rescales as T1, T2. So if we rescale this by this, T2, 3, 3, 2, 3, and T3, T1, 3, 1, okay? We have to come out with a function so that we must get T1 squared, T2 squared, T3 to the -2, and the same function back. Is that impossible? Yes?
Don't you also need the listings to come out right? So those two things can contradict each other.
Well, I mean, as a function of only three variables, I can call these variables x, y, and z. All I need is this to happen. Is there any function, any rational function of x, y, and z that will do this?
No. Isn't this equivalent to us for transformation that leaves 3 points fixed?
No, I think you're probably thinking too much.
Okay. I guess there's nothing.
I have a function of three variables. Call them x, y, and z.
X
And I
squared, y squared over z squared?
Whatever.
So what would be?
1, 2 square, x squared, y squared over z divided by z
X squared, y squared.
divided by z squared.
So your proposal, if this is x, y, and z, your proposal is to put 1, 2 squared,
That doesn't work.
Like you need to make your outgoing velocity
2, 3.
Probably you can make something like 1, 2, 3, 1, 2, 3.
So this is your proposal. Does it work? I don't think so.
1 over x times y times z.
Sorry?
1 over x, y, z.
1 over x, y, z.
That's not going to be x, y, z.
No, because your elicities go with -2. But I mean, you can
over y, z.
Okay, here is another proposal. X cubed over yz. This is 1, 2 cubed over 1, 3, 3, 2. Does it work? Yes, we're done. We computed it. Cannot be anything else. So we just got the amplitude up to a constant. And what is the dimensionality of this constant? Let's look at the most general dimensions for the amplitudes. If we plug the total number of particles to be 3, what do we get? Or the little n to be 1, what do we get in that formula? We get that this object should have mass dimension m, right? You know what I'm talking about?
Not anymore.
No.
From there,
I mean, I want to compute. I mean, this guy is a particular case of the top line, right? It's an amplitude. It's an m,
okay, yeah.
right? I want to know the dimensionality that it should have,
Okay, yeah.
right? So if we plug in that top formula, little n to be 1, or the total number of particles to be 3, I get, what do I get? I get m, right? M to the first power.
Yes.
Very good. And what is the dimensionality of this thing here? It's m2.
Yeah.
So this is dimensionless. And this object, which measures the strength, remember, this is basically kinematics here. I mean, but this thing that measures the strength of how these things interact is called the coupling constant. And in this particular case, it's dimensionless, which according to our general philosophy of life is a very important condition. I mean, no, it's just nice. Okay, are we ready for the general case now?
Quick question.
Yes.
So didn't we say last time that in order to have the helicities work out, you have to have?
Sorry, can you say that again? That in order?
In last time we said in order for the helicities to work out correctly, you need the like the brackets to appear twice as many times as the helicities, either in like the right numerator or denominator.
No, this is what I said. The two. We needed the overall thing to be twice. Right? Because each bracket, each guy contributes only a t. But we need twice as the helicity of the particle. In other words, yeah, that's right. Okay, so we're ready for the general case. So note what we're about to do, right? We're about to compute an infinite number of amplitudes. How nice is that? Well, so we have H1, H2, and H3, okay? Well, how do I start? Well, it must be a function of, say, it's only a function of these brackets. Well, I don't know what the answer is, but any function of these three brackets must be something that I can write as, sorry, I'm going to use this notation now. I don't know what the answer is. I'm just going to find it. I'm going to put every possibility. Okay? And I'm going to put coupling constants x, y, z. I know that only one of them, at most, I think, only one of them will be non-zero. My job is to find which one that is. Okay? In this particular case, we did already, right? We found that only 1, 2 cubed, 1, 3 to the minus 1, and 3, 2 to the minus 1 was a magic combination, right? We found x to be 3, y to be minus 1, and z to be minus 1. So that was a magic combination, and thus we found the answer. But now we're doing the general case. So what do we find? So under the rescaling, so when we rescale, we find that this term goes into what? Goes into t1 to the x plus z, t2 to the x plus y, and t3 to the y plus z. But we need this thing to go to t1 to the 2h1, t2 to the 2h2, and t3 to the minus 2h3, 1, 2x. So for the right combination of x, y, and z, this must be true. So that gives me 3 equations. So I say x plus y is equal to 2h1. Now x plus z, x plus y is equal to 2h2, and then y plus z is equal to minus 2h3. Now this is a moment you all have been waiting for. You open your laptops, open Mathematica, plug this in Mathematica, and say solve for x, y, and z.
You can add all 3 and then you just...
Yes, I know. Thank you. It was a joke. But I did it in Mathematica, just in case. So I found that x is h1 plus h2 plus h3. Y was minus h1 plus h2 minus h3. And z that's it. We're done. Okay. Now, only one term contributes. The solution is unique. So we know what the answer is. Where this represents our Mathematica output, the solution that we found. Okay? Of course, again, there is an overall number we cannot fix, which is the coupling. Very good.
Is there a way to fix the coupling somehow?
No? No. You can measure and fix the coupling. But there is a little catch here. I mean, we're all very excited. We computed an infinite number of objects. However, there is a catch. Well, there are 2 things we have to say. First, that there is also the other solution, right? We should also have started everything with the square brackets and not with the angular brackets. Do we have to redo the whole calculation? No. What do we have to do? Yes, just the solution we found for x, y, and z, now we just put a minus sign, and then we get the right answer. That's excellent. So this could have been this, or another coupling. Let me call it G tilde. Very appropriate. 1, 2 minus x star, 2, 3 minus y star, and 3, 1 minus z star. Okay?
Stars being the specific solution.
Yeah, stars, these are the stars. Very good.
Something, we're still thinking f as a rational function, right?
Yes, but in this particular case,
Okay.
there is nothing else that you can construct, because if you had a logarithm, say, right, the argument of the logarithm has to be something that is little group invariant under the rescaling, right? Because if we rescale the inside of the logarithm and we pick up a factor, the amplitude would transform as something that picks up an addition to it, right? It's a logarithm. If the argument is rescaled, we're going to pick up something that is an addition to the object, not a rescaling. You agree?
The argument is rescaled. We pick up.
If the argument, suppose this function was a logarithm.
Yeah.
If the argument of the logarithm is rescaled, what we pick is an addition to the amplitude, because we apply log of a, b, right?
Yeah.
Very good. And that's the wrong transformation. We need something that rescales, not that picks up a contribution and addition, right? Now, is there any invariant that we can make out of these three objects to be the argument of the logarithm? So we now need something where we get 0, 0, 0. So we have to set this to 0, this to 0, and this to 0. What's the only solution? Exactly. The number 1, meaning that x is equal to 0, y is equal to 0, and z is equal to 0. But log of 1 is 0. So we just found the answer, the full answer, not even in my rational function approximation. This is all it can possibly be.
Okay.
Yes?
Elicities can be half integers, right? So there's a possibility that my function should have something like 1 over square root of something.
Excellent. That's very good. Helicities could be,
But
that's right.
that-
Helicities could be half integers, right? But then, if we get something that doesn't look like a rational function, right? There is something strange going on. So those guys, we set their couplings to 0, and we say, well, those things don't make any sense. Because they have, no, because if they have square roots, how do you define them? On which branch do you define them?
Right.
They are not well defined, right? And that's how you discover that you cannot have just a particle of helicity plus a half producing 2 particles of integer helicity, because that will produce square roots. You need at least 2 half integers.
So somehow
So we are discovering a lot of things just by playing this game.
Sorry.
somehow you're imposing by that conservation of the helicity, or
No, there is no helicity conservation, right? I mean, the sum is not 0.
right, but I mean, if it's an integer, it has to be an integer after the scattering, right? I mean, you have
No, you can have a half coming in and then producing a half and a 1,
okay.
right? Okay, so we are learning lots of things. And, okay.
So particles with not half integer helicities will not work because our rational functions wouldn't involve square roots, etc.
Yeah, that's right. So if you get a square roots, we should set those couplings to 0. Okay, so what was the other possibility? Or g tilde 1, 3, 2, 3, 1, 2 cube, right? Now, I've been making a lot of excitement about the fact we computed all these amplitudes, an infinite number of them. We know all of them completely. There is nothing else they could have been. However, there is a little catch, right? Now somebody comes and tells you, look, but come back from your cloud, from your complex momentum space thinking, and go back to the real momentum. So what happens?
It breaks down.
Well, yeah, that's very interesting. One of the 2 solutions give me the right answer, and the other one does something completely crazy. What is the right answer that I should get? 0. That's right. Because for real momenta, I don't have 2 solutions. I only have 1 solution, which is everybody equals to 0, right? So what happens to this guy when I set these brackets to 0, when I take the limit when they go to 0? 0. What happens to the other solution? So the other solution is not physical. So I'm done. All right, very good. Now we go back to complex momentum.
So, sorry. The way we're supposed to use these to get information out of, we're supposed to be combining these things to get something physical out somehow?
Yeah,
I mean,
so
you
now,
said you factorize things into these guys and then you try to compute something useful out of it.
right, so very good. So now you're saying, well, you seem to be wasting our time, so why don't we do something useful with this? Thank you, yes, that's a very good suggestion. And that's what we're going to do. Okay, the first observation is the following. Let's take our friend there. But I'm going to write it as in our old way of thinking about it. So we have our, actually to save time, let me write PA with helicity 1, PB with helicity 1, then we had our T, and we have our PC with helicity 1, 2. And we got this nice thing there as the only thing that it could be. Now, can anybody see something wrong with this formula? Well, there is something wrong, that there must be a momentum conservation here, but let's forget about it for the moment. But there is something wrong with this formula. These particles have helicity 1. We haven't discussed this, but we think about them as bosons. Okay? Now, if they are bosons, what happens to their wave function if I exchange them?
Shouldn't change.
They shouldn't change, right? Very good. So I exchange them. So this is identical. So what happens to that side?
Goes for a -1.
Can everybody see that we get a minus sign? So we have to set G to 0.
So your notation there should be P11, P21, and P31, right?
P31. Yes. Thank you. Yes. So we have to set G to 0. So what do we learn from here? Yeah, you look disappointed. After all this,
Maybe
we
if
think
you
we're...
combine two of them, you get your minus sign.
Yeah, so you say, well, let's first analyze what we got. We said, well, a single kind of helicity +1 particles cannot interact. That's what we found. Now, I told you that we think about this as photons. If you take Maxwell theory, okay, without electrons in the theory, we discovered that the theory is free. The photons don't interact. Okay? So we just learned something that we know is true. So photons, in a theory that doesn't have electrons, don't interact. Okay? So photons don't interact. And it's just because it's impossible to make something that works. Okay? But now we can say, well, but this result is too good to just let it go. I mean, we have something very powerful. What if we put several kinds of particles? Not just one kind of photon, but let's imagine a theory that has several kinds of photons. Okay? So imagine a theory or a world with several species of helicity 1 particles. Okay? So we have to come out with a label for that labels the kind of particles, right? You know, I'm not very good with the labels. I haven't done a good job. But I'll propose the following. I'm going to use capital letters A, B, C, and D as the labels of the species kind. Okay? Yes?
How would introducing additional species of helicity 1 particles allow us to rescue the situation?
Good question. Yes. Well, because that's right. That's right. Now they are not identical, right? But if they are not identical, we can still allow this coupling to depend on the species label. Because now we have to give another label here. We have to say particle 1. Sorry, I'm going to go back to my A, B, and C and B, because it's hard to write capital numbers. Okay, so I came out with this notation in the morning, so I cannot change it now. It's going to be too hard. So we have this H, A, and then PB, HB, and B, and then PC, particle of the kind C, and then I'm going to write here different species of particles can interact in different ways, right? We know that from Lorentz transformations, this is the only kinematic way that they can have, but the couplings could be different. So given that we have these guys on the left, I'm going to put them together here. I'm going to put the other label here just to remind myself that is the guy outgoing, okay? Times our universal factor. Very good, that's right. So all I have to do in order to make sure that my amplitude doesn't change under the exchange of the labels, making such a mess here. This is AC and CB.
This is for HAHB equals 1, right?
Yes, only in that case, yes. Thank you. It's good that you guys are paying attention. Clearly, I'm not paying attention. So this means that if we declare that these coupling constants satisfy this, then we're back in business.
B, A.
Thank you. Again, yes. Okay? We don't have to set them to 0. Yes.
You say the helicity 1 particles are bosons. Right?
Yes.
We're taking that for granted?
Yes.
Because
We could derive that from unitarity, but that at this point, let's just take it to be the case. Yes. Sorry. Well, but that's something we know. I mean, it's at least intuitive.
It's intuitive with spin. You know?
I know,
With
yes.
helicity.
Yes, that's right. But you have also in your condensed matter courses have taken the photons, I guess. Well, not photons. Well, phonons to be bosons, right?
But, well, that follows.
Yeah, well, no, it doesn't follow. Yeah, I agree. But
So in that extent, you can say that some particle that has helicity 1/2 or 3/2 is a fermion?
yes.
What effect would the mass have on the symmetries of the wave function?
Sorry, just to say something to finish that thought. Okay, the connection between the kind of helicity and the statistics is called the spin statistics theorem, right? And I encourage you at the end of the lecture, well, of course at the end of the lecture, but I encourage you at some point to see if you can prove the spin statistics theorem, meaning the consistency of that the theorem is required for the consistency of the scattering of particles, just using the principles we have laid down in the course, okay? And if you do, just from what we said, then I think you can write a nice little paper. Okay? I can give suggestions for the title. And then we will be co-authors.
Just one add up.
Yes. Sir.
This is probably really naive, but so what Andreas is saying that you can't that you couldn't take for granted the fact that helicity particles with helicity 1 could be bosons, but we know particles with spin 1 are bosons. But helicity is a term you're using for massless particles, right? Which is
yes.
So using the spin statistics theorem for these particles, I mean, where does the mass even come in when you're using the spin statistics theorem, or does it come in for the waveform?
I told you that the spin is a name that they also give to the absolute value of the helicity. Remember?
Yeah.
Yeah.
That's your explanation.
We have. Okay, so but if we.
So the spin statistics theorem applies to things with a spin, and I told you that people call the absolute value of the helicity spin, and therefore it also applies to that. Okay, so let's actually try to understand or compute something that is not zero in our world, right? Not in my imaginary world, literally, of complex momenta. Okay, so let's imagine a 2-to-2 scattering. Okay, so exactly what we have over there. So we have particle A with helicity 1 and a species index A. So this is a particle of kind A, B, 1, B, C, 1, C, and D, 1, D. Okay? Very good. So what do we want to do? Well, let's try to constrain this function as much as possible from what we know, okay? From the scaling properties, from dimensionality, from crossing, and unitarity. Well, the first thing we concluded was that any function right here, here, right? Any 2-to-2 scattering has to have this form, okay? These guys are massless, so we get an STU times a numerator, which is a polynomial in lambdas and lambda tildes, right? Now, what polynomial could that be? We need this thing to scale properly under rescalings. These guys, right? So what is it supposed to do? It's supposed to scale as TA square, TB square, TC to the minus 2, and TD to the minus 2. Do you agree? If you look at the helicities, that's what it's supposed to do, times itself. Can anybody come out with a simple function that is just a polynomial in lambdas and lambda tildes that would do the job? Clearly, these guys don't do anything. We concluded that they are invariant, right? These guys don't transform, so they cannot help us in accounting for the rescaling. So something else has to do it. Well, imagine you want these guys. These guys look easy. A and B square. AB square. Let's just put an AB square over that. But I said I need a polynomial because unitarity told me that the only poles this thing has are these three. So how can I fix that then? Square brackets. Excellent. Okay? Now, if I check dimensions and I get the dimensions right, I declare victory and I'm done. Okay? Which would be convenient. But, well, let's see. So the dimensions. This guy should be dimensionless, right? That was special about 2 to 2. What are the dimensions of this thing? So the S has dimensions of mass squared. So we get 6 powers in the denominator, right, from the 3 guys. And we get, what do we get in the numerator? This guy has dimension of mass, so we get 4 powers in the numerator. Well, this is 2 powers, and this is 2 powers. We get 4 powers. Well, it could be the coupling constant, but from unitarity, we know that when this factors, it will have to factor and only contain 3 particle amplitudes, which we know already have a dimensionless coupling. So we wouldn't want to do that. So all we have, the only possibility is to put a polynomial here that compensates for the dimensions. So we need a polynomial that has dimensions of mass squared and do not transform under rescalings. So it has. Very good. So you could try S plus T plus U. But that sounds a little bit arbitrary, right? I mean, you should allow for something here. Let's call it NS, NT, and NU. Now, these things do not depend on any kinematics at all, right? We have fixed everything. There is nothing that we can do. So these guys can only depend on couplings. And in the last 10 minutes, we are supposed to find out who they are. Okay? Okay. Sorry? Yes, I'm just deciding what to erase. I think we can erase this now.
Can you also have?
I'm sure I'll regret it.
Can you also have AB in triangle brackets times AB in square brackets?
That's us.
Also doesn't scale. So is that? Oh, that is okay.
Okay. So what else can we use to constrain this function that is on the blackboard? I'll give you a hint. It's on the top blackboard.
The composition of the check.
Yeah, the name for that would be the constraint coming from unitarity. Let's use unitarity, okay? So unitarity tells us that if we take our function A, B, C, D, and we take the limit when S goes to 0, remember PA plus PB squared goes to the mass of the objects we're considering here. They are massless. So we take them to 0. These things should go into AB particle Q 1 over S. So it must have a divergence. So it must have a pole in 1 over S. C and D. Okay. Now, we derive unitarity, right, from putting a completeness relation. So we were supposed to sum over all one-particle states. So if this guy belongs to the species Q, remember my brilliant notation is that capital letters denote the species type, okay? So if there are many kinds of particles, I'm supposed to sum over all of them. That's what unitarity tells me, right? So I have to sum over Q. Whatever number of species I'm introducing, we don't know yet how many we're putting in, but we have to sum over Q. This guy is our friend capital A, capital B, capital C, and capital D, okay? And we said this guy is of helicity 1, 1, 1, and 1. We are also supposed to sum over all possible helicities that our internal particle can possibly have. But for this exercise, I'll just take it to be 1, 2. Okay? So I'm just going to assume we have these particles. Okay. So let's compute it. I don't see people writing and doing the calculation. So do you expect me to actually? Well, we have the answer over there, right? So we have the answer for the left-hand side here. 2 guys with plus helicity coming in, and the guy coming out with plus helicity. Okay? So we know already what this side is. Okay? So what is this? So we have sum over Q, and we write this. We have our fancy coupling constant, ABQ, right? Let me put this a little bit higher, times these factors. So what do we have? We have AB cubed divided by AQ, QB, okay? That's this thing. That's great. Times 1 over S times this guy. You say, oh, we haven't computed this, right?
It's the same thing.
You can use cross.
But yeah, that's right. Exactly. So we're in business because we have CD, Q, and then just CD cube, CQ, QD. Very good. Now we apply the same thing here. So this, when it goes to S equal to 0, what is the term that dominates? Clearly, this guy with this guy cancels, and this is subleading, so it doesn't contribute to the pole, to the divergence. Only these 2 guys, okay? So we get something of the form AB squared CD squared over TU times NTT plus NU U. Now, you also had an exercise where you had to show that S plus T plus U was something in general, right? But it was proportional to the mass, right? Here, these are massless particles, so this is 0, okay? This is in general true for massless particles. But we're in the limit when S goes to 0. Now, when S goes to 0, T goes to minus U.
You're missing an S in this expression.
Yes, thank you. Very good, yes. That was the most important one. Okay, so in that limit, this is true. So what do we find here? This simplifies us to NT minus NU times T. Now, this minus sign is going to be very important for us. You will see why. Okay, so now we have this formula. Let's write everything in terms of our brackets, in terms of our spinors. Okay. So we have AB squared CD squared over. Now this T cancels this T, so we get only the U, right? And the U in our notation is A and D, right? So we get AD times AD. This is U times NT minus NU 1 over S. All right? So we're almost there and almost on time. We're supposed to compare that to this. But this is the same as the sum over Q, capital Q of G ABQ, G CDQ times a kinematic factor. Well, we have the 1 over S times something that looks like AB cubed CD cubed over AQ QB, CQ, QD. Okay?
I'm lost a little bit. We're considering the momentums to be real here?
The momentum, no.
No?
No.
Then how is it that the complex conjugate of your diagram is the square brackets?
Because this guy is now on the left. If you look in your notes, now this guy has to transform as t to the 2hq. And these guys will transform. And there is only one solution, right?
Okay.
And there is only one solution that doesn't blow up when I become sensible and go back to real momentum.
Okay, it's not by the fact that when you consider real momentum both the
No, I'm not.
these and these are the complex conjugate of
Now, remember, these three particle amplitudes are uniquely defined.
Okay.
Okay? Very good. So I'm almost done, except that these two things look very different. Extremely different, I have to say. That might be an inconvenience.
There's a 1 over S.
There is a 1 over S. Good. That's the spirit, you see? Very good, very good. That's the spirit. Okay. Now you will see why I decided to tell you how to write these things more explicitly. Let me take a factor from the denominator, AQ. Okay? Just that little factor over there. I use my hockey stick. This factor. And I'm going to take this factor away. Okay? I'm going to put a minus. I'm going to put this as Q C. Actually, is that smart? No, it's not smart. I could just take the other one. This one. And this guy. Okay? Now, this looks fairly strange. However, I'm going to write them explicitly as lambda A, alpha, lambda Q, beta. Okay? Now there is an epsilon contracting these two guys, right? That's how I get the determinant. I'm going to write this guy explicitly too. Q gamma lambda dot. If you want to be pedantic, you have to write the dot there, and rho dot D, and put an epsilon contracting those indices. Okay? Very good. Now, what is this object that appears here in psi? Does anybody recognize it? Is the entry of the 2 by 2 matrix defining Q. So this is what I call the matrix Q with entries beta, gamma dot. Okay? But momentum conservation tells me, remember this matrix was defined to be the vector Q contracted with sigma. Now I can replace Q by the difference, by the sum of PA plus PB. Do you agree? By momentum conservation. That's true. So if this is true, when I put it in here, the matrix Q is the same as the matrix PA plus the matrix PB. And I can use that here to say that this is a matrix PA beta gamma, or that entry of the matrix, And therefore, I get the following. I get, when I use this one, again in terms of lambdas and lambda tildes, I get A with A, and then A with D. When I use this one, I get A with B, and B with D. Now, what is A with A? It's a determinant where the two rows are the same. So it's 0. Okay?
I didn't get how you went like after from here on to the right hand side.
Okay? So that's what that is. Now I can take the other combination. So take the other combination, which is, let me actually put it here, CQ, QB, that's the other one. These two, no, sorry, yep, this guy with this guy. And what do you get in this case? That's what we get, right? Because now we expand this out. Q, we replace it again by PA plus PB, okay? But the PB term is the one that is going to drop because there is a B here. So the BB term gives me 0, and only the A survives, okay? So let's use that in our formula here and see what we have. And then we cross our fingers and hope that something nice happens to this. So the numerator is AB cubed CD cubed divided by the product of these things we found. So we found on the top line AB, BD, and here we found CD, or sorry, CA, AB. Okay? You agree? Now, what is this? This guy cancels 1 power. We get AB squared from here and from here. This guy doesn't look right, so we just keep it there. Over BD CA. Oh yeah, that's right. I have another one. That's very good. So you would say, oh boy, this really looks bad.
Couldn't you
You still need to divide by the
that A in the terms on the right?
Sorry, I could do what?
Couldn't the CAAB have been a CDDB instead?
You mean flipping this?
Yeah, since
Well,
instead of
before we panic, or before I panic, and you enjoy the view, let's see how far we are, right? Whenever you want to see how far you are, you take the ratio of the things and see what happens, right? Okay, so let's take the ratio. So what's the ratio? So we want to take that thing, AB CD cubed, divided by BD, and then CA, and divided by this thing, okay? Well, dividing is the same as putting this guy in the numerator and this guy is in the denominator, so I'm going to do it. I'm going to put AD here, AB here, and then this guy is here, and this guy is here, and compute this. Okay? So this guy cancels these powers. Okay, what else? This guy cancels this. So I end up with CD, AD, AD over BD, CA, AB.
I think what Nico was saying, I think, was that in the momentum conservation for CQ, QB, instead of replacing Q equals A plus B, just write Q equals C plus D, and you'll get everything.
Okay, very good. Well, we can do that here, right? Yeah. If we didn't make any mistakes, what you're suggesting, we could do it here.
Q equal to C plus D.
So what you're suggesting is that, well,
The thing is that you're also missing the other denominator here to compare, right?
well, what if?
But don't we have exchange symmetry? Like you can exchange D with B and you end up with the same thing. Because
Let's apply, well, I think, just 1 second. Let's actually do something similar to what you're saying. Let's actually replace this again by what it is, right? As a momentum PA, and use momentum conservation for the other guys. So this guy is going to be replaced by the sum of C, B, and D. But C contracted with C is going to give me 0. B, when it contracted with B, is going to give me 0. So only the contribution D will come, and I'm going to get a minus sign. Okay? That's just by doing exactly what I did there, but using momentum conservation for the four particles, okay? The overall momentum conservation. So if I use this, what happens to my ratio? So I get CD, AD, AD divided by BD. So I apply that to here, so I get a minus sign, CD, DB. Okay? Well, it doesn't, I mean, it looks good, but not that good.
and there's an AB also there at the end. In the denominator you had BD, you split up. Oh, sorry, my bad.
This is the thing I
Yeah.
okay. But what was this? AD, AD. What invariant was that? This invariant was AD, well, I can write it as PA plus PD squared, right? How about the denominator? It's almost in the form that I want, right? It's almost DB, DB. So you have to flip this sign. So you get a minus sign, I get a plus, and then I get PB plus I get PB plus PD squared.
So there's a dot.
Sorry? Oh, well. How did this happen?
So why did you write PA plus PB, PD not PA dot PD?
Where?
The invariance,
Yes.
CA.
It's the same, right?
Oh, I see. Oh, because there's some squares.
It's U over T plus.
Can anyone see where the mistake was? Sorry? Where?
Are we still working with S equals 0?
Yes. Oh, thank you. Awesome. Thank you. I was going to offer something, but luckily I didn't do it before you said it. I was going to offer a reward for that. That's excellent. Okay, very good. So, isn't that great? So we found that this thing is actually minus the other thing. So we conclude that this thing has to be minus this. Okay? So you'd say, well, so what? I mean, we suffer so much just for that. But let's actually combine two little things and we're done. So our conclusion from studying the unitarity of AB going to CD was that what we call NU minus NT has to be equal to the sum over Q of AB Q G CD Q. Okay. Now we use crossing and check. So this was the factorization when S went to 0, implied this. By just switching labels and using crossing, we can conclude that when we take T to 0, we're going to get something very similar to that. You just have to change the labels, and you're going to get NT minus NS, okay? Remember, we're just switching labels. So you can switch the labels and conclude that this gives you this.
How do you get an
How do you
NT
get
rather
the
than
NT?
How did I get what?
It should be NU, right?
It should be U.
Sending U to 0.
Sorry, in the U channel. And in the T channel, oh, by the way, these are called channels. So people talk about this as the S channel, this as the U channel, and this as the T channel. And then you get the conclusion that NU minus NS is equal to the sum over Q, G CAQ, G ABQ. Now, recall that we don't know anything about these couplings except that they are antisymmetric. But now we have found something interesting. They have to satisfy a constraint. Why would that be the constraint? So if you want to solve these equations and you put them in Mathematica, Mathematica will tell you cannot solve for all variables. Why would that be? You probably haven't had that experience of Mathematica telling you that. Yes, sorry?
linearly dependent?
Because they are linearly dependent. What is the linear dependence?
Well, sum of the first two.
Just add them up, right? If you add up the three equations, well, in fact, it's good that we cannot fix everything, right? Because there should be an overall constant. But add up all three equations, and you find that this guy, I told you the minus sign was going to be important. This guy cancels this one. Oh,
Cancels minus delta.
so actually I copied it incorrectly. This guy cancels this, and this guy cancels this.
And that.
Why are we missing a D in the last equation?
We're missing a.
You're missing a D in the last equation, you got 2 A's.
Oh yes. Cannot believe I can. I'm copying this from here, and I got it wrong. If I just derive it, probably. Yes. So we get that whatever these couplings are, okay, unitarity plus crossing and transformations under Lorentz imply that these couplings must satisfy the following. This side is 0, and therefore this sum over Q has to be this. Okay? So the conclusion is that unitarity plus crossing plus Lorentz, all that imply immediately that if you have several species of helicity 1 particles, they can only interact if their interactions satisfy something that is called a Jacobi identity. And therefore, all possible interactions of a spin 1 of helicity 1 particles are governed by Lie algebras. Isn't that nice? So if mathematicians had not discovered Lie algebras before, we would have. Yes?
So that means that if you have more than one species of spin 1 bosons, then we are forced to introduce internal symmetries.
Well, it was already, yes, it was already here, where we said that a single one didn't work, and needed couplings that satisfy this. In particular, it's telling you that can you have only 2 species? No. How many you need? The smallest number you can possibly have. 3. Have we seen that in nature?
I don't know.
You don't know? Yeah, but it's reasonable because we actually, at low energies, at the energies where we live, we only see photons, right? But people in accelerators, which are our microscopes, they have actually been able to see more things. And they have seen a particle called W plus and a particle called W minus, particle called Z. And of course, we can see, well, photons, okay? At even higher energies, okay? These guys actually come from, let me call them gamma A, gamma 2 and gamma 3, and another guy, let me call it B, okay? These 4 guys, already we know that if at very high energies they behave like massless particles, they cannot possibly come from something that is a group of 4. It has to split somehow. And in fact, it splits as a group of 3 and 1 guy, okay? And these 3 guys form the Lie algebra of SU2. They interact with couplings that precisely satisfy the Lie algebra of SU2. And due to our friends, the Higgs, at low energies, or lower than those energies, they let us see 3 massive guys and 1 massless guy, which is a photon. This guy here, we say that it has a U1 symmetry group, okay? Now, this is great. So U1 is the simplest Lie algebra that you can imagine. SU2 is the next one. Do you think, have we seen SU3? I mean, that would be the natural question, right? So SU3 needs 8 guys. And yes, these are precisely gluons. Okay? Have we seen SU4? No. SU5? No.
This result comes from the fact we consider complex momentum, right? This.
Yes, indeed.
So how can you reconcile the fact of having complex momentum with reality?
No, but this was to constrain a rational function, right?
Right.
But our rational function in the end, the one we constructed in the end, can now be taken for real momenta, and it gives an answer. Okay. It's not vanishing. So we got an answer. Okay. We actually computed the answer that is measured in experiments. So you put in there gluons, and you produce a differential cross-section that is the thing that is measured. Okay? Okay? Yes?
Where did the H come from? I'm sorry.
The H. Oh, the H is the